Well, in this video we're just going to take a little bit further from the previous video, the function we got from previous video. So we stopped at here, which is the general formula of the Fourier series. And the brilliance of Fourier, Joseph Fourier, is that he figured out a way to get the constants, which is a0, an, and bn. So he said if we let the period equals to 2L, then that would be true. And now we're going to talk about trying to do the application of it. And by the way, about the application, I've seen this, I've been in where you are before. In the application is that when you graph it, that's actually when you see it come together, because when you take that function and apply this formula, these constant a0 and a of n, which is a1, 2, 3, 4, depends on how far you can go. But when you graph it, it's going to go like this on your calculator. It's going to go like this, and then there's this squiggle here, and then come down all the way down here, and then squiggles, and then come up, and then squiggles, and then come down, squiggles, come up, squiggles, and so on. And the more number you do, the more constant you solve for, like a1, 2, 3, let's say 10, and b10. Actually, a is here actually because it's cosine. You've got an odd function. A is not going to count. But in general, the more constant you do, these squiggles would become smaller and smaller and smaller until you can't actually see it with naked eye. You're going to have to zoom in with the calculator to be able to see the squiggles. So it's really amazing. Okay, now I'm going to do the first one, which is find out a0 for this periodic function. But before that, let's just determine the period. As you can see, this is well, the period in this case is from minus pi to pi, right? Because it goes up. Sorry, it comes from here down and up, and that's one period. From here to here, that's one period, right? Like this. So that's one cycle, which is the period. So from minus pi to pi. So in that case, pi equals to 2L, and 2L is 2 pi. That means the period is 2 pi in this case, and L is pi, half of it. So the formula of a0 is 1 over the period, which is, in this case, let me just put that aside. Yep, it's a lot of pages. So in this case, our a0 is 1 over the period, right? So the period here is pi. Sorry, 2 pi. Because it's from minus pi to 0, and then from 0 to pi. But by the way, we can't actually model it the whole thing together because it's not a continuous function, it's a step function. So we have to break it up a little bit, break it up into two. So we model it from here to here, this piece, and then we model it from here to here. That means we model from minus pi to 0, and then 0 to pi. So that's what I'm going to do with a0. So a0 is going to be 1 over 2 pi, and then over open bracket, and then we take the integral, which is we agreed that it's going to be from minus pi to 0, right? We model it from here to here first, and then from here to here. So we start with this, and then the f of x. Well, the f of x here is minus c, right? Because we're trying to model minus c, integrate this bit of minus c. So f of x is minus c. Obviously it can be minus 1, minus 2, but c is just a short for constant, dx. And then plus the integral from, well, in this time from 0 to pi, and then positive c dx. And if we solve for that, we will see that a of 0 equals to what? Equals to 0. Yep, 0. You know why? Well, if you look at that, we would see that from this to this, it's minus, right? The area from here to here is minus, and here it's the same area, but it's positive, so they cancel each other out. As simple as that. So a0, but only in this example, though it's not always 0, but in this example, it's 0. Now we're going to try to do the same, break it up for a of 0, 1, 2, 3, 4, and for bn 1, 2, 3, 4. But if you guess what the a's are going to be, 0. You know why? Equals to 0, the whole of a's, so we don't have to do it. You know why? Because it's, as we said before, because it's an odd periodic function, not even function, because if we multiply, or if we apply it even, or the cosine function, it looks off the phase, it just doesn't match it, so it wouldn't model it at all, it would be working against us. So a of 0 would be 0, a of n, sorry, the all of a of n's will be 0. You can actually apply that, but due to short of time, we're just going to try and solve the b of n's now. Again, here we substitute the original formula with what we've got here in the graph. So the period is 1 over pi, that's the period. Half the period is 1 over 2 period, which is 1 over pi for b1. And again, we integrate by breaking it up into 2 from here to here, and then from here to here. So that's what we did. Integrate minus pi to 0, and then minus c, which is the constant, and then sine x dx, because that's b1, that's the original formula, right? That's b1, by the way, plus from 0 to pi, the second bit. But before that, you might want to question, what about this? Well, if we substitute n with 1 and L with pi, well, the pi would cancel with the pi, and is going to be cosine, sine of 1. So, because it's b of 1, so n is equal to 1, right? And L is equal to pi. So let's just put pi would cancel with the pi, so we're left out with x. So that's how we've got sine x dx. Alright, if we integrate that, this definite integral, we would get sine x here, minus c here, sine x with, if we integrate this bit, we get minus c times minus 2, right? Because it's below the x-axis, this bit. Same thing for here, if we apply the definite integral, we get plus c times 2, because it's above the x-axis. And the minus would cancel each other out. Minus times minus is positive, so it's going to be 2c plus 2c, and that would equal to 4c. So now looking back at the original formula, we times it with 1 over pi. So the whole thing, so 1 over pi times 4c is going to be 4c over pi. So that is our first b. If we apply the same thing for b2, what you do is just substitute the ends with like 1 with 2 and so on. So here, if we substitute n with 2, would end up with sine 2x. So yeah.